Good morning. I would like to recap a bit what we did last Friday. So we started concretely discussing bifurcation theory or dynamic system theory for ordinary differential equations. So here's the general setup. We have a vector of dynamic variables, and we have a vector of control parameters, and then also a vector of nonlinear functions. And we would like to understand the solution space of these ordinary differential equations. And the point was that we would like to have a geometric characterization of the flow of the solutions in phase space. And in particular, we would like to know when this flow in phase space changes on a qualitative level, not a quantitative level, really having a different kind of geometric structure. I started out with a very simple system, namely just a one-component ODE with only one parameter. So remember, this was the normal form of the equation that we studied. And basically, what you do is you study how the flow changes of a parabola as you go with the parabola from a situation like so, where there's no intersection and the flow is just to infinity, to a bifurcation point, and then it splits into two fixed points, one stable one and one unstable one, and you represent that in a bifurcation diagram where you plot the fixed point as a function of the control parameter, that's mu, having one stable branch and one unstable branch. And I told you this is a pretty generic situation for a one-component system, because you always locally can look at a function like a Taylor expansion that's made explicit here, and this then happens typically when you change parameters in a one-component system. So remember, these are saddle node bifurcations. There was a second type of bifurcation that I motivated with the theory of phase transitions. So remember, here we have a Landau potential with only one minimum above the critical temperature and two minima below the critical temperature. When you then study this as a function of temperature, which is this parameter R, you can again do a bifurcation analysis, and what one finds is that above Tc you have one stable fixed point which becomes unstable below Tc, and instead you have the emergence of two stable fixed points corresponding to the two possible values of the magnetization in a ferromagnet. And that's called now a pitchfork bifurcation, and to be precise, it's called a supercritical pitchfork because the pitchfork emerges above criticality. That's usually called the second order phase transition in the language of statistical physics. And you can also flip things around such that you have this type of scenario where for parameters r less than 0, you do have one stable fixed point and two unstable fixed points, and then they merge into one unstable fixed point, and that's called a subcritical pitchfork because this pitchfork is below the threshold value of r. All right, that's a recap of last time. And what we would like to do now is to go to more complicated systems, which is now what happens when we go to two control parameters instead of just one. But I'm still staying with the case that I have one dynamic variable. And that will lead us to what's called Cusp Bifurcation by stability and what's also sometimes called catastrophes. Okay. So what will I choose? So I'll take as an example to show you how this works a normal form, and this normal form reads like so. Its dtu is a parameter r times u minus u to the third, and then plus h, and that you can also write as minus du f of u, where you have a f of u being equal to minus r over 2 u squared plus a fourth u to the fourth and minus hu. So you can read this either mathematically, saying this is just the normal form, that's the math we would like to study, or you can read it more in the language of a thermodynamic problem, where f of u is a free energy landscape for a Landau function. And this says that we have this double well or single well potential. I've changed now the sign. This is minus r instead of r. So for r being greater than 0, this will have a double well potential, and for r less than 0, this will be a single well potential. And that's just what we had on Friday. And now I'm saying I add to it an external magnetic field, and this external magnetic field breaks the symmetry explicitly, right? So here you have a u to minus u symmetry. Because of that term, you have an explicit breaking of the u to minus u symmetry. So you can read this as an Ising model with a external magnetic field that I call H. All right, and now we would like to study what happens. So maybe first pictorially, if you have a free energy landscape, f as a function of u, there's of course the case where you just have a single minimum. The one which is more interesting for us is the one where you have two minima. And I'm drawing this for h equal to 0. And obviously, right, if you add an external magnetic field, you break that symmetry, so you make this minimum a little lower or this minimum a little lower. Okay? Right, so for h being different from 0, you have something which then maybe looks like so, and this here is then proportional to the value of h. Okay? So now let's study that problem. And the way to do that is that we look at the fixed points equivalent to equilibria in the thermodynamic sense. So we have this function little f, which is a function of u and also of the control parameters, which is r times u minus u to the third plus h. And I want this to be 0, and then I will get the fixed point values, and I will get them as a function of the control parameters, which are r and h. If I want to decide on stability, I just have to look at the derivative. That's something we learned yesterday, Friday, I mean, and evaluate that at u star. And there you get, if you do the simple math here, that this is r minus 3 u star squared. And if this is less than 0, then this is equivalent that you have a stable fixed point, and otherwise you will have a unstable fixed point. Good, now let me draw this, and I'll use the slides for that. So if you look at that, then graphically you can construct the fixed points by saying I look at the intersection of a horizontal line given by h with this cubic that's given by RU minus U to the third. So let's look at a graphical solution. Which is the intersection of a function y1, which I call minus h, and a function y2, which of u, both of them, which is r times u minus u to the third. Okay. Now let me just show you that, because it's very simple to show you that explicitly. Sorry. So here we have this problem of finding the zeros of that function, and graphically it's this competition between the magnetic field and the term coming from driving it to the minima of the lambda potential. Then you have two cases corresponding to a single minimum in the lambda potential and a double well. So for a single minimum, this function RU minus U to the third is just a cubic that's monotonically decreasing. And because it's monotonically decreasing, I have intersections with y1 equal to h that are unique. So we have just one type of fixed point, and this one type of fixed point in the limit of h going to 0 is just our non-magnetized state. And as you switch on the magnetic field and push it up or down, then you see that the corresponding magnetization just goes linear in the external magnetic field, as you would expect. Okay, that's very different when you are at parameters which are in the low temperature phase, where r is greater than 0. When r is greater than 0, the slope here at 0 is positive. Okay, and then the u to the third term pulls you down to the right and pulls you up to the left. So you have this typical N-shaped structure in this graphical representation. And now you can study what happens here. So if h here is larger than some critical value, you see again you have just one intersection, so you have a unique fixed point. And then as you move down, as you lower the amplitude of the magnetic field, you reach a point where this horizontal line is tangent to this maximum of the N-shaped cubic. And then at this point, you have a bifurcation. And you know the bifurcation already. This is a saddle node bifurcation. Instead of having no fixed point, you have the emergence of a stable fixed point and an unstable fixed point. And by the way, so if you look here at when do you have a fixed point or not, you can read this off here from this line. So f prime being less than 0 is a stable fixed point. That's equivalent to y2 prime being less than 0, because y1 is just a constant. Right? So if you look here at the branches where this function y1 is monotonically decreasing, you have to have a stable branch. If it's monotonically increasing, like here in between, it's an unstable branch. And as you go down here to the right, it's again monotonically decreasing, so you have a stable branch. And you can repeat the game, right? If you go then down, these two fixed points here, in addition to this observing fixed point, then you have a stable fixed point and an unstable fixed point. Lowering h, they will move together, and then here once this is horizontal to that minimum, the two fixed points will merge and they will vanish. This is then an inverse saddle node bifurcation. Right? So that's what we have here. Now let's write down the equations for that. So the equations are such that the saddle node bifurcation happens, right, when there is a tangency condition, and that means you do have a fixed point, so f is 0, and you have f prime being 0. So your tangent in this graphical plane, and we can work this out. So from that relation, you get the value of the saddle node bifurcation, just reading it off here. So you have, from f prime equal to 0, we can read this off here, sorry for that. So from f prime equal to 0, you see that u star equals to r over 3, the square root of it, and you have two options, plus or minus that value. So from that, you get u saddle node plus or minus is equal to plus or minus square root of r over 3. And of course, this now refers to r greater than 0. And in the language of a ferromagnet, this is below the critical temperature. Okay, we can substitute this in f equals 0. So again, you look down here. This is our second condition. This is for tangency. This needs to be a fixed point. So I just insert what I found for u star in this relation and solve it for h. So I get an explicit relation for h. So from that, we get h at the saddle node plus or minus as a function of our parameter r equals r times u saddle node plus minus u saddle node plus minus to the third power. And when you insert of what you have for the saddle node bifurcation, this will give you plus or minus 2 and then r over 3 to the power 3 over 2. And that I define to be plus or minus the critical value hc of r. Okay, and what we have found by doing that are the two lines in the space of h and r where a saddle node bifurcation happens. Okay? And let me now show you how this looks like in a plot. This is now our HR plane. So vertically we have the external field, and horizontally we have the parameter r. In the paramagnetic phase, there's only one stable fixed point, and these two lines, so the upper branch and the lower branch, given by plus or minus hc of r, this r to the 3/2, gives the boundary of the regime where you have bistability. So you can see this is a stability diagram in the language of nonlinear dynamics. It's a phase diagram in the language of critical phenomena, where here you have a monostable phase, and here you have a bistable phase. So it's a phase transition to ordering as you go into this bistable regime. What's quite remarkable is that this is quite singular here at this point. So you see there's a cusp because you have r to the 3/2, and this cusp here is characterizing that this is a very particular and special point, which you can visualize more clearly when we go to a three-dimensional representation. So instead of looking in planes, I look here in full three-dimensional space. What do we have here? We have here the dynamic variable, and here on the plane we have the two parameters, control parameters, that change the equilibrium values. So here R, again, is whether you are above or below the critical temperature. Here you're above, here below. And this here tunes the external magnetic field. And this surface here, or manifold, is the surface of equilibrium points, or the surface of fixed points. So let's call this the fixed point manifold or equilibrium manifold. And this manifold of equilibria is smooth, right? So there's no kinks or anything like that, but it has a fold. Like if you would fold a piece of paper, you would get such a fold. And this has the following interpretation. So let me again recap what I already said. If we are at a value of R greater than 0, that's a discussion we had here on the board. So you fix yourself to be below the critical temperature, and then you flip these curves around and plot U as a function of H. And then you can either go on this graph or that graph. Let me explain it here first. So as you start from a magnetic field, which here is 0, you'll increase the magnetic field. There's a saddle node bifurcation where you have a jump to the other branch over there. And then as you would reverse the magnetic field, you have another jump at a saddle node bifurcation, and you go back. And that's a hysteresis effect, as you might already know from thermodynamics. So as you increase and decrease the magnetic field, when you have a temperature that's away from criticality, then the system first remains on a branch of your order parameter, which is U less than 0. And then it jumps to the other one. And in between, you have this bistable regime. And as you tune the parameters slowly, you will get these hysteresis effects between the two different equilibria. We can look at this here in the same way. So let me now start from the top. So here you have a high magnetic field. So you have a positive magnetization. You're on that part of the fold. Here you approach on this fold the saddle node bifurcation, and then there's a catastrophe because this is no longer stable. You fall down to the other branch, like here, and now on the other branch you can go up, and again you then have a catastrophe and you jump to the other branch. So if you now trace out all these saddle node bifurcations here on this plane, or here in the corresponding projection in the RH plane, you have this cusp, which is this curve of saddle node bifurcations on the plane. That's rather smooth, actually, right? It's only the projection that gives you this kind of cusp, as you can see here, right? So if you have these things merge at this particular point and project it down, that's our cusp here. Yeah?
Is it correct to say, if you want to establish an analogy with dynamical systems in classical mechanics, for example, is it correct to say that the RH plane is similar to the phase space plane where I have...
Exactly. I mean, this is the same concept. So in classical mechanics, you also learn about phase space, where you typically plot in phase space the position and the velocity. And then you have phase space representation of harmonic oscillator. That's the same kind of thing. So that's taken over. And sometimes, I guess in your course or in many other people's courses, at the end of a classical mechanics course, sometimes you study nonlinear dynamics, where you go away from the Hamiltonian dynamics that you study first. We have conservation laws, conservation of energy, etc. And that's the difference here as well, right? We no longer have conservation of energy that's different. So we look at dissipative systems, and that's why the attractors of dynamics are very distinct from the attractors that you have in a Hamiltonian classical system. But the idea and concept of phase space, same idea.
And if we want to follow this analogy,
yeah.
When we pass in the three-dimensional graphic representation, we have the dynamical variable on the z-axis.
Mm-hmm.
What would be the analog in classical mechanics of this kind of representation here?
It would just be, if you have a pendulum, you just look at the pendulum of a damped harmonic oscillator. That would be the corresponding variable, and you know what it does. It does this, and then it goes to the fixed point, which is just being quiet at a position 0 because there's damping. Okay. That would be the equivalent representation, which is just be one point. Mm-hmm. Because here I'm looking only at the fixed point. So the final steady state, not the time evolution towards that steady state. So if you wanted to know how the system relaxes from an initial configuration, you would need to draw the flow here in this type of phase space. So for example, if you are here, somewhere there, then since this is stable, you will flow to the manifold and you will stop here. If you're somewhere there, in between, right, you are in a non-stable regime, so you flow up. And in particular, when I argued that I'm here at the saddle node bifurcation, the system dynamically transitions over to this branch because now you are beyond the regime of stability, so dynamics no longer has a steady state here, so it needs to evolve temporally up to the upper branch. Right? Other questions? Yeah, and there's one special point, as you realize. This special point is a very singular choice, namely that you choose H to be 0. This is what you then call a second order phase transition. In this diagram of bifurcations, it's a very singular limit of the bifurcations that we saw, right? All the other points, if there's a bifurcation, is a saddle node bifurcation. Only here, if I'm cutting through this diagram at H equal to 0, so right here, I'm getting a pitchfork bifurcation, where if I again look here at the graph, which is not the full 3D, but a 2D projection, so you start from here, you go from here, there's a stable fixed point, and then in a pitchfork bifurcation, it transitions to an unstable fixed point and two stable branches to the right and to the left. That's the singular limit of a second order phase transition or pitchfork bifurcation. All the other transitions here are first order or saddle node bifurcations. Yeah?
In the example that you gave with the magnetic materials and the hysteresis branch we have, in these materials it is closed, the hysteresis branch. It's like beginning from somewhere and ending in the same point, if I remember correctly.
I'll say it again, I didn't quite get.
In the magnetic materials, if I remember correctly, these kind of branches begin from some point, and according to changing, and while we change the field, it goes through different states and ends up again in the state that we began. Here, the system ends up in the state that we begin first, or it could end up on a different state, sit on one branch of it, or.
It depends. So, right, so let's say we are in a world where thermal fluctuations are very small. Then, if I'm taking that picture, this is the thermodynamic state if I'm starting with a magnetic field. So if I fix the magnetic field here, and if I'm in a regime where I'm below this dashed line, right? Because below this dashed line, there's an unstable fixed point. The flow is to that fixed point. So it would mean for the thermodynamic system, if for some reason the initial magnetization in your system is below this dashed line, then the dynamics, the thermodynamics of the system drives you towards this kind of steady state. If you're slightly above, so here, if that's the starting point, let's say here you have a zero magnetization here, then the dynamics of the system would drive you to the other fixed point, which is the other thermodynamic state. Okay? Now, as you add thermal fluctuations to it, the system can flip between those two states, but only if the systems are small, right? If you have a very, very large system, then the likelihood of getting a thermal fluctuation that kicks you over the barrier to the other thermodynamic ground state goes to zero in some power of the system size. Right? If you write here at the zero value, then fluctuations are very important. They are kicking you back and forth between the two equilibria. Now let me go to the second order phase transition. So once you're here, where h is equal to 0, then fluctuations obviously have to be important in the close vicinity of r equal to 0, because there the two branches are very, very close. They become infinitely close as you approach r equal to 0. And that's where thermal fluctuations are crucial. And the picture that I have here on the board with a mean field theory starts to fail. Then you need to account for fluctuations, and that's done in the theory of critical phenomena and the corresponding renormalization group calculations that you would need to characterize the thermal behavior close there. You know, but there's such a huge space of other parameters. It's interesting and nice to look at particular properties in the vicinity of this tiny cusp, but there's so much more physics surrounding this tiny cusp. Other questions? All right, so that concludes the chapter on saddle node bifurcations and cusp bifurcations and all that. And let me now come to another case of bifurcations, which is called a transcritical bifurcation. And this will also give you a short introduction to what in statistical physics is called the context process or infection dynamics. It is a very simple model, but it already shows you some key features of infection dynamics. So let's say we have two individuals that we call M and we call C. Let's say the individual M is in some way sick, so it carries a virus, and the individual C doesn't carry the virus, so we call it healthy. And then we imagine that we have a well-mixed environment which means that everybody is interacting with everybody at the same time. That seems like a strong assumption, but you all know there's a famous virus spreading experiment happening every year in Munich called Oktoberfest. And there in a tent, this assumption is pretty well, a pretty good approximation for spreading of a virus, and that's why we have what's called a Wiesengrippe, and some of you might have had this kind of grippe. So let's say we have that. Then you can look at what can happen. So if a sick individual meets a healthy one, it will transmit the virus with a certain rate that I call lambda. So this is the infection, and lambda is the corresponding rate of infection. You, of course, if you are sick, you can become healthy again, and that happens with a rate delta, and that's called recovery. And as you can see, this is a very mild virus. There is no death event happening here. Everybody that gets infected also gets healthy again. Now, how would you write an equation for that? Well, you just write down an equation for the density, the number density of your sick and your healthy individuals, and you translate this reaction scheme. This is what it is. It's a reaction scheme. You translate that into what's called rate equations. Well, you don't really talk about each individual agent that's in your tent, but you say on overall the total number of healthy individuals and the total number of sick individuals evolves according to a certain law. Well, here we have, if M meets a C, right, so proportional to the density of healthy and sick individuals, infection happens. So I multiply this with a rate lambda, and that means with a rate lambda, if a healthy and sick individual meet, they increase proportionally the number of sick individuals. You lose here, or you become healthy again with a certain rate delta, and that's minus delta times m, because each one of those sick individuals becomes healthy at a per capita rate delta. For the second line, I need just to write the opposite, because this is an infection process. So what used to be a healthy individual becomes a sick individual, and therefore I have a minus, and you become healthy again with a recovery rate m. So here you have actually a plus sign. So that's the dynamics that we have that we need to analyze. Now you should realize when you look at this set of rate equations, there's a conservation law that you already saw from the reactions. There's no birth and no death, so meaning the total number of individuals will not change. And you can read this off here as well. If you add up m and c here, the right-hand side cancels. So dt n is 0, meaning that n equals m plus c is a constant. Because it's a constant, our dynamics is not really a two-component dynamics. It's a one-component dynamics, since I can eliminate one of the two variables in this equation. So let's do that. And I will eliminate such that I'll focus on the individuals, the number of individuals that are sick. So this is then lambda. And now I'm inserting here that c equals n minus m. So that means this is c times m times n minus m minus delta n. And now I'm rewriting it a bit. So I can write this also in a form where I take the m out, and then I have here lambda n minus m minus delta, and that I call my nonlinear function f of m. You can easily read off the fixed points here. That's really a very trivial exercise. One of the fixed points, I call m1, is the one where m1 star is 0, and that's simply the state where the population in our Oktoberfest tent is healthy. There's no sick individuals. And the other one is the 0 that you can read off from this second bracket in the nonlinear function f of m. So that would be our second fixed point m2 star equals n minus delta over lambda. Those are the two states, and now we can plot as a function of different parameters when this transition happens between the two fixed points. Okay. So maybe the first thing we want to realize is that, again, the stability of the fixed point is determined by f prime. So f prime of m equals lambda n minus 2m minus delta. And from that, if I look at f prime of m1 star, just insert here 0 on the left-hand side, then you get lambda times n minus delta. So now you see quite straightforwardly when this fixed point is stable or unstable. It's stable, so m1 star is 0, is stable if this is negative, and that means the population size has to be such, so let me write this down, this is negative, for n larger than delta over lambda, and it is positive for n smaller than delta over lambda. Do I get this right? Yeah. So now let me look at this graphically. So let's look first at the left-hand side and ignore the right-hand side. So what we do here is we ask when is the fixed point, what fixed point for m is stable as a function of population size. And what we found by the analysis is that if the population size is smaller than this threshold value, delta over lambda, then m1 star is the stable fixed point. So the virus doesn't spread in the population. If the population is large, right, then the likelihood of a virus spreading also intuitively should be much, much larger. But the point is there's a threshold. Above this threshold, the virus is spreading in the population. So the fixed point here is m1 star, different from 0, namely n minus delta over lambda. That's one way of seeing it. So as you increase the population size, so the number of people in a tent, then the likelihood for spreading the virus is high. Okay, makes sense, right? On the other hand, you can also ask the same question for a different parameter. You can ask now what happens for this bifurcation when I keep n fixed, but I change the corresponding parameters delta and lambda. So remember, delta is the recovery rate and lambda is the infection rate. So let's say we go to delta equals 0, nobody recovers. right, then obviously you have an outbreak of the infection in the population. And you need to reduce increase the recovery rate. That's hard to do because those things are kind of hardwired in people, how fast they recover from a virus, basically 2 weeks. And lambda is the infection rate. As you decrease the infection rate, you can make the corresponding virus spreading in the system vanish and go back to a healthy population. Okay? And of course, infection happens if people meet, and that means you have to reduce the number of times people meet, and that then gets you out of a population that has a virus in it. All right, so let me stop here and have a break. And after the break, we then look into systems with 2 components, 2 dynamic components instead of 1 dynamic component.